Recall that a vector space can have many different bases, and certain bases are more convenient than others. For example, the vector space R2 has the convenient standard basis given by the vectors 1, 0, and 0, 1. That is what we call the standard basis for R2 because it has special characteristics that are particularly useful. One important characteristic is that the two vectors are mutually orthogonal. They are perpendicular. Another important characteristic is that each vector, 1, 0, 0, 1, is a unit vector, vectors of length 1 with respect to the usual dot product. In this video, we identify some advantages of bases consisting of mutually orthogonal unit vectors. First, definitions. So throughout, we assume that V is an inner product space with inner product as shown. So again, V need not be Rn. The inner product need not be the usual dot product. Okay. So given a set S of vectors in V, say with elements V1, V2 up to V sub n, we will call S an orthogonal set if any two distinct vectors in S are orthogonal. In other words, the inner product of V sub I and V sub j is 0 whenever I and j are distinct. If S is orthogonal, and in addition, each vector in S is a unit vector, we will call S an orthonormal set. So remember that when defining a unit vector, we need the notion of length. And remember that in an inner product space, the definition of length is determined by the definition of the inner product. A set of orthogonal vectors which forms a basis for V will be called an orthogonal basis for V. And similarly, a set of orthonormal vectors which forms a basis for V is called an orthonormal basis. So for instance, in R3, the standard basis with elements E1, E2, E3 is an orthonormal basis with respect to the standard inner product. Okay, so E1, E2, E3 are mutually orthogonal with respect to the usual dot product, and these are unit vectors with respect to the length defined by the usual dot product. And in general, for Rn, the standard basis is an orthonormal basis with respect to the standard inner product. In R3, considered as an inner product space with the standard inner product, this set is an orthogonal set because the dot product of 0, 1, 0 with 1, 0, 1 is 0. The dot product of 0, 1, 0 with 1, 0, negative 1 is 0. And the dot product of 1, 0, 1 and 1, 0, negative 1 is 1 plus negative 1 or 0. So it's an orthogonal set of vectors, but not an orthonormal set because 1, 0, 1 and 1, 0, negative 1 are not unit vectors with respect to the standard inner product. But the set S, as shown, is an orthonormal basis in R3 considered with the standard inner product. So you can check that the dot product of the first vector with the second is 0. The dot product of the first vector with the third is 0. And the dot product of the second vector with the third vector is 0. So it's an orthogonal set. And each vector is a unit vector with respect to the standard inner product. The length of this vector is the square root of 1 plus square root of 2 squared plus 1 plus 1 over square root of 2 squared plus 0. Square root of 1 half plus 1 half is 1. And similarly, you can check that this guy and this guy has length 1 with respect to the standard inner product or the dot product. So it's an orthonormal set in R3, and it's an orthonormal basis because you can check that these three vectors are also linearly independent and forms a spanning set for R3. Consider M22, the set of all 2 by 2 matrices endowed with the Frobenius inner product. Recall that this inner product is defined as follows. Inner product of AB equals the trace of A transpose times B. So here, the set S containing these two matrices is not orthogonal because if we compute the inner product of the two, the trace is, rather the value of the inner product is 2, which is non-zero. But note that the set containing these 4 vectors is an orthonormal set in M22 with respect to the Frobenius inner product. So I leave this as an exercise. And in fact, because this is an orthonormal set and it's a basis for M22, then it is an orthonormal basis for M22. In P2, which is the vector space of all polynomials of the form AT squared plus BT plus C, where A, B, C are real numbers, let's consider the inner product as shown. The integral from 0 to 1 of f times g with respect to t equals f comma g. Recall that P2 has basis given by the polynomials t squared t1. For these vectors in P2, we have the following inner product computations. This is the inner product of t squared and t with respect to this. This is the inner product of t squared and 1. This is the inner product of t and 1. So observe that none of these values is 0. So which tells us that B is not an orthogonal basis for P2. It's a basis, but it's not orthogonal. Note that only one vector in this set is a unit vector. So you can compute for the inner product of each vector with itself in B. Okay, the inner product of t squared with t squared is 1/5. Inner product of t and t, 1/3. Not the length of t squared is the square root of this value. Anyway, it's not 1. Similarly, the length of t is the square root of this inner product. It's not also 1. Only the vector 1 is a unit vector in B. Here are some remarks about orthogonal sets and orthonormal sets. So note that if S is a finite set of vectors with elements v1, v2 up to vk, which is an orthogonal set, and S does not contain the zero vector, then S is linearly independent. Okay? An orthogonal set of vectors that are non-zero is always linearly independent. And you can verify that easily, because if we assume that R1, R2 up to Rk are scalars, such that R1 V1 plus R2 V2 down to Rk Vk equals 0, then for each I running from 1 to k, the inner product of V sub j with the zero vector is 0, but the zero vector is the same as this linear combination. So this inner product can be expressed as the inner product of Vi with this sum, then applying the definition of an inner product, this sum can be expressed as this sum. And because we are assuming that the V's in S are orthogonal, if I is not equal to J, V sub I and V sub J has inner product equal to 0. So what remains in this sum is the term, okay, which is given by Ri multiplied by the inner product of Vi with Vi. Because Vi is non-zero, not the zero vector, then this is not the zero vector. We are actually applying the property or a property of the inner product. So this tells us that Ri equals the zero scalar. Yeah, this should be the zero scalar. So because I is arbitrary, we conclude that Ri equals 0 for all I, showing the linear independence of these vectors. But we should note that the converse of this statement is not always true. It's not necessarily true that if you have a linearly independent set of vectors, then that set of vectors will be orthogonal. Finally, from an orthogonal basis, we can actually compute or determine an orthonormal basis for an inner product space. Okay, so if B is an orthogonal basis, so mutually, or the vectors in B are already mutually orthogonal, so we just need to find vectors in a basis which are unit vectors. And to do that, we just divide or multiply each vector here by the reciprocal of their length. Okay, so V1 multiplied by the reciprocal of its length will give a unit vector. This is actually the unit vector in the direction of V1. And similarly, this will be the unit vector in the direction of V2 and so on. So this will form an orthonormal basis for V.